This is the first video on Chapter 41, Integral Theorems. And so the first theorem that we're going to look at is Theorem 321. And as I've said before, there are things in math that work the way we want them to, and there are things in math that don't work the way we want them to. This is an example of something that I think does work the way we want it to. And so the integral of a constant times a function is the constant times the integral. That is part 1 of Theorem 321. Part 2 is the integral of the sum is the sum of the integrals. And the part 3 is the integral of the difference is the difference of the integrals. I'm going to outline the proof of part 2. Then I'm going to modify that slightly to show you how to prove part 1, and then we'll talk about part 3. So for part 2, we start with the sum of the integrals. Now, I didn't state the theorem, that's in your notes, but remember, part of this is f and g are known to be integrable to start with. So we know that this integral exists and this integral exists. So we start with the sum. Well, what's the integral from a to b of f of x? We just use the definition where we're chopping the interval up into n congruent pieces and we're using the right endpoint. So this is what we do for the integral from a to b of f of x dx. Plus, well, the integral from a to b of g of x dx. Same definition. We're going to chop the interval up into n equal pieces and we're using the right endpoint. Now, we know that the limit of the sum is a sum of the limits, and so that's why we can combine this. And we know that we can add. Addition is associative and commutative, so we can add things in any order. So I skipped some steps algebraically here. But essentially, once you look at this, you can put it all back together so that you just have, as I said, the limit of the sum is the sum of the limits, and we can sum things in any order. And so the sum of these two limits becomes this limit. And then this is simply the integral of f plus g of x dx. I'm going to step out of the frame for a moment so you can look at this and take your notes. Then I'm going to come back in and show you how to essentially create the proof of part 1. Okay, so I didn't want to make a whole separate video to go through the proof of part 1 because we can easily modify this proof to get the proof of part 1. So first of all, we just have the integral of c times f of x dx. So we're going to ignore g. And so we have the integral of c times f of x dx. And we're going to scratch out g because we're ignoring g. And so what does that equal to? Well, we just have c times f of x. Again, we'll scratch out this line because we're ignoring g. And c, because multiplication distributes over addition, can be factored out of the sum. And because the limit of a constant times a function is a constant times the limit, then the c can come outside of here. And we'll just scratch out g because we're ignoring g. Again, the c factors outside the sum, then the c factors outside the limit, and then what does that make? That makes c times f of x dx, and we're scratching out g. Because all I'm doing is I'm slightly modifying the proof of part 2 to give you the proof of part 1. 3 actually is simply a consequence of 1 and 2, right? So if we have the integral of f minus g of x dx, part 2 says we can write that as the integral of f of x dx plus the integral of negative 1 times g of x dx. And then part 1 tells us we can factor the negative 1 outside the integral sign to get this. So 3 is really just a way of, if we want to prove 3, we simply combine 2 with 1, and that will give us 3.